Hi class, we are now looking at section 5.4, covalent bonding. Looking at covalent bonding, this is when when non-metal atoms combine, they do so with covalent bonding. In covalent bonding, two electrons are shared between two atoms. Consider the bond that forms between two hydrogens. Each hydrogen has one proton and one electron. We represent it with a Lewis dot symbol on the sketch above. So you can see here we have one electron being symbolized here, or you can look at the drawing here with the protons and the electrons. To form a covalent bond, two electrons pair up in the space between the nuclei. The force of attraction between the nuclei and the two electrons holds the atoms together. We represent these shared electrons by drawing a dash between the chemical symbols for hydrogen. So when you see a dash, as you see here, when a dash is in between the two chemical symbols, that means this represents two electrons. It's more of a house cleaning. It's easier to write out than writing it like this. It's cleaner. So remember, the first energy level only holds two electrons. By forming a covalent bond, each hydrogen atom completes its valence level. And we talk about octets, but for hydrogen and helium has two electrons. We call that a duet. So this fills a duet, which is two. And that makes it more stable because it now takes on the configuration of helium. So when two hydrogen atoms combine, they form a molecule. Earlier, we defined molecules as groups of atoms that bind together and behave as a unit. The bonds that hold molecules together are covalent bonds. In its elemental form, meaning how it's found, hydrogen is a gas composed entirely of these two atom molecules. So when hydrogen is found in elemental form, it's found with two hydrogens together. That's what the H2 is. So it's a hydrogen molecule. So when the non-metal, a lot of this I'm going to repeat here. A non-metal atom combines, they do so with covalent bonds. That's what a covalent bond is sharing electrons. And I wrote down here a duet, because it takes on the electron configuration of helium. Consider the bond that forms two hydrogen atoms. Each one shares its electron with the other. That creates a covalent bond. And the force of attraction between the nuclei and the two electrons holds the atoms together. These shared electrons are drawn as a dash that represents the two electrons that are shared. Okay, now let's look at fluorine. So looking at bonding that occurs between two fluorine atoms, each fluorine atom contains 7 valence electrons and therefore needs only one more electron. To complete its valence level, two fluorine atoms can share 2 electrons to form a single covalent bond. By forming this bond, the atoms fill their valence shell with 8 electrons and satisfies the octet rule. So if you count here, this is 2, 4, 6, 8. That satisfies this octet. 2, 4, 6, 8. That satisfies this octet. So both fluorine atoms now fill the octet. We use a dash to represent 2 shared electrons in the Lewis structure. Lewis structures depict the arrangement of valence electrons within a molecule or polyatomic ion. Look more in, we're going to look more into Lewis structures in chapter 9. So now let's look at 7 elements that form diatomic molecules. Hydrogen and fluorine are 2 of the 7 elements that exist as diatomic molecules. That means that how they're found. They're found joined with another of the same of what it is. So there's 2 of them. That's what di means. Di means 2, so diatomic molecules. And there's 7 of them found this way in their elemental form. And so the 7 means that you can draw a 7 here. You can see the 7, which is not really a 7 because there's the 7th one. But if you kind of look here, you can see that there's a 7 that's drawn out on them. The others are nitrogen, oxygen, and the rest of the halogens. So as a trick to help you remember, notice that the nonmetals besides hydrogen that behave this way form the shape of a 7 on the periodic table. Okay, so atoms sometimes have to share 2 or more electrons or even 3 pairs of electrons in a covalent bond. They have to do this in order for each atom to fulfill the octet. So we represent double bonds using 2 dashes between the atoms and triple bonds, triple covalent bonds using 3 dashes. So remember, when you see one dash, that means 2 electrons. So we have 2 here, so that means 4 electrons. And here we have 2, 4, 6. So this means 6 electrons in this triple bond. Okay, so now we're going to start looking at compounds. Covalent compounds form when elements combine through covalent bonds, forming molecules. Water is an example of a covalent compound. In a water molecule, an oxygen atom covalently bonds to 2 hydrogen atoms. The valence level of each hydrogen is filled with 2 electrons. The oxygen has 4 unshared, so you see there's 2 here, 2 unshared electrons, 2 pairs, and 2 covalent bonds. Between the unshared and the shared electrons, oxygen has 8. There's 2, 4, 6, 8, and then hydrogen fulfills it with having 2, which it does on both of these. So everything is filled the way it needs to in its valence level and fulfills the octet rule for oxygen and the duet rule for hydrogen. Let's take a look here. How many electrons does nitrogen atom share through covalent bonds? How many of the valence nitrogen electrons are not shared? Does this nitrogen atom have a complete octet? So let's take a look at this. In the Lewis structure, each dash represents a 2 shared electrons. Nitrogen forms 3 covalent bonds to hydrogen. Each dash represents 2 electrons, and nitrogen has 6 electrons. The 2 dots above the nitrogen represent non-bonded, unshared electrons. Combining the 6 shared and the 2 unshared, the nitrogen atom has 8 electrons in its complete valence shell. So that's 2, 4, 6, 8. So it means it has a total of 8 from the 2 unshared and the 6 that are in the dashes. Okay, so covalent compounds. We describe covalent compounds using molecular formulas. This type of chemical formula gives the actual number of atoms in the molecule rather than the simplest whole number ratios. Consider hydrazine. Hydrazine is the fuel for rocket thrusters. A hydrazine molecule contains 2 nitrogen atoms and 4 hydrogen atoms, which is N2H4. The empirical formula for this compound is the smallest whole number ratio. So the easiest way to describe this is that we use empirical formula when we're also dealing with ions. But when we're dealing with molecules, there's a way to try to explain this. Empirical formula is very similar to a skeleton. We all share a skeleton, but our molecular makeup is what makes us all look different. So there's a lot of compounds that all share the same empirical formula. But once they start getting the molecular formula, they're all very different. That's a maybe too simplistic way of explaining this. But the molecular formula is hydrazine, and the empirical formula is what it's built upon. That's the foundation, so that's why I call it the skeleton. But there's other formulas that will also come from NH2. So let me go back one more. So covalent compounds often lead to complex structures. You know what? I don't want to do that one yet. Hold on. I don't want to cover what I just covered. Okay, so in total, how many valence electrons are represented in this Lewis structure? So let's count them. I always count the bonds first. 2, 4, 6, 8, 10, 12. So it's going to be 12. 4 pairs, which are 8 electrons. 2, 4 pairs, unshared, sorry. 2, 4, 6, 8. I was like, wait, that's not 8. And then 4 pairs, 4 electrons here. In this structure, does nitrogen fulfill the octet rule? Well, let's count. 2, 4, 6, 8. Yes, it does. Does oxygen? 2, 4, 6, 8. Yes, it does. Hydrogen also, it only takes 2. So yes, it does. In this structure, how many shared and unshared electrons surround the nitrogen atom? Well, we have 2, 4, 6. So we have 6 electrons that are shared. So it's going to be either B or C. And we have 2 electrons that are unshared. So that's going to be C. All right, so now I jumped ahead. Covalent bonds often lead to complex structures. Look at the molecule octane, a component of gasoline. One molecule of octane contains 25 different covalent bonds. Larger compounds may contain hundreds or thousands of covalent bonds. Because of this complex bonding, elements can often combine in many different ratios. Each unique bonding arrangement produces a different compound. This table lists several of the compounds that have formed between phosphorus and oxygen. So this is where I talk about empirical. If we break these down, some compounds will come from the very same empirical formula, where and then build out from there. So now we're going to look at naming binary covalent compounds. Binary means two. Covalent compounds containing only two elements are called binary covalent compounds. These compounds are named in a manner that is similar to ionic compounds, but there are differences. Let's look at these two. We have PCl3 and PCl5. When naming binary covalent compounds, we first identify the element that is further down or to the left of the periodic table. So that means the ones closest to the metals. This element is named first, and the full atom name is used. So in this example, we use the name phosphorus. So phosphorus is going to be first because it's closer to the metals. The element to the right is named second, and that's the one that's closest to the noble gases. And that is going to be the anion. So we add the "ide" ending to it. We name the second atom, in this case, chloride. We're looking at so both of these have chloride in them. Because covalent compounds form different ratios, we use a prefix before each element to indicate the number of atoms of that element present in the molecule. And the first element contains only one atom. So if it only contains one atom in the first element, this is a rule for the first one only, then by default we don't use the word mono. We just leave it off. So we just would say phosphorus instead of monophosphorus. But if it's for the second one, we do use it for the second naming, for the anion. Based on these rules, then we're going to call this, because we add a prefix in front of each element. So we have phosphorus, 3 is tri, so phosphorus trichloride. We have 5, so we have phosphorus pentachloride. And the name tells you how many are there. These are for covalent nonmetals. All right, so this is my slide from another book. This is just giving you the structure. So you have a prefix. Unless it's 1, then we don't use it. Name of the first element, don't change anything. Prefix for the second one, and then change the ending to "ide." And these are covalent, means nonmetals. And here I'm giving you another breakdown. You need to know the prefixes you're required, because the naming is also something that's never going to leave you in chemistry. Here are some common molecular formulas. You can see carbon dioxide, carbon disulfide, nitrogen oxide, dinitrogen oxide. These are those weird rules where we don't use mono in front of them. You know, I just taught you a rule, and now I'm taking back some of the rules. And I know there's always exceptions, unfortunately. Sulfur dioxide, sulfur trioxide. Okay, now we have to cover this kind of housekeeping. So when we use these prefixes, what we notice is that sometimes two vowels will line up together, and we don't want that. So if the root name begins with a vowel, we remove the A from the prefix. Just remove it. And we keep the vowel from the other one. So for instance, phosphorus pentachloride, we didn't need to do anything here because it's not a vowel that started here. But with oxygen, there is. So we had to take the A away. So this is diphosphorus pentoxide, not pentaoxide. That would be wrong. We remove the vowel that goes with the prefix. Okay, so practice naming. Nitrogen and oxygen form two covalent compounds, NO2 and N2O4. Name each. So in this case, this is nitrogen. We don't use the word mono. Nitrogen dioxide. And the second one is dinitrogen tetroxide. We took the A off of the tetra. Name the molecular compound NCl3. So the first one's going to be nitrogen. This is for another class. I broke it down step by step. So the first one is a nonmetal, and we determine it's a nonmetal, so it's nitrogen. And name the second metal, we have to by using the first element, and then what followed by ide. So we have chloride, not chlorine. And now we have to add a prefix. So in the second one, we have 3, so it's nitrogen trichloride. Name the molecular compound B2O3. Again, just going step by step for my other class. It's a nonmetal, it's boron, so nothing changes with that. Name the second metal by using the first name followed by ide. It's oxygen, we cut that off at the Y, so it's oxide. Now we're going to add the prefixes. So we have 2 for boron, which is di, and we have 3 for oxygen, which is tri. So the name is diboron trioxide. However, The vowels I for tri and O can be next to each other. So it's trioxide. Write the molecular formula for diphosphorus pentoxide. So we figure out what element they are. There's phosphorus and oxygen. We have a di in front of phosphorus, which means 2. And then we have 5 for oxide. So we use the subscripts, and that's P2O5. Name these covalent compounds. So I'm just going to put these out here. Dinitrogen tetrafluoride, sulfur dichloride, carbon tetrachloride. The correct name for the covalent compound BCl3, so I'm going to say it's boron and chloride. There's 3 of them, so it would be boron chloride. That's wrong. I didn't even catch that. I apologize. They gave me the slide. That is not right. It is boron. There's a 3 here, so it would be D. Boron trichloride. I'm going to repeat this a few times. Boron, this is totally wrong. This is boron trichloride. What is the correct name for this? So we have 2 nitrogens and 4 fluorides. I'm hoping it's right. Dinitrogen tetrafluoride, that is correct. So in summary, in covalent bonds, atoms share electrons. Covalent bonds form between nonmetals. Most covalent compounds form discrete molecules. That means water is H2O. We describe molecules using Lewis structures and molecular formulas. Naming binary covalent compounds, the leftmost element is first. That's the one that's closest to metals. The second element is the one that's closest to the noble gases. That's the anion. Prefixes indicate the number of atoms present. That is a big difference from naming ionics. We do not do that. And this is a chart from one of my other books. So now we've covered ionic and molecular. We are going to learn later about naming